Hello guys, and welcome back to another video. This is the introduction of a new series on this channel about linear algebra, and this is where we're going to start our discussion of linear algebra. So we're going to start by why matrix vector multiplication is defined the way it is. We know that given a matrix, we multiply it by a vector and we get somehow another vector. So we're going to discuss all of these ideas, and I haven't started from the basic introduction to linear algebra. When you take a look at the Gaussian elimination method for solving linear systems, because there are countless of videos on YouTube, and I thought I didn't need to make another video about this topic, and so I wanted to start from matrix vector multiplication, and this is a very important topic. So we all know that linear algebra begins with trying to find a way to solve linear systems in a compact and clever way. So for example, here we have a system of two equations, two simultaneous equations, and we basically need to find the unknown x and y such that these two equations are true simultaneously. There are countless of methods for solving this equation, and countless of methods to look at this equation, what this equation actually means. So, the first thing you might think when you see two equations like that is, okay, I need to find x and y such that the both equality are true simultaneously. And there might be, for example, in this system, there's only one solution, and we're going to take a look why it is that there's only one solution. But we should take a look at the geometry picture in order to understand the algebraic picture. And what is the first geometry picture that comes to mind? Well, firstly, let's take the first equation and let's isolate the variable y, so we can bring y to the other side. So we get y equals 2x minus 1. For the second equation, we have y equals 2 minus 4x plus 2. So what are these? These are the two simultaneous equations written in another way. So we isolated y. Why have we isolated the variable y? Because this reminds us of functions. Y is a function of x. Each of these equations is a function. So we might plot these two functions on a graph. They're also very simple because, as you can see, they are lines, straight lines. So if we draw the two lines, we can pick 2 points and just draw them. So for example, for y equals 0, let's now focus on the first one. So I'll draw the first one in green, so you can recognize the 2. So if we put x equals 0, we get y equals minus 1. So at the value x equals 0, y equals minus 1. Whereas when the function, for example, we could pick another value of x, for example 1, 2 minus 1 equals 1. So for x equals 1, the function has the value 1. So this is x equals 1, this is 1, and this is the point 1, 1. So we know that for 2 points, there's only one straight line that goes through both of them. And sorry, I had to draw the line in green. All right, now let's take a look at the second one. When when x equals 0, y equals 2. So when x equals 0, y equals 2, that could be here. And when x equals 1, we have minus 4 plus 2 is minus 2. So for x equals 1, its value is minus 2. So it goes through this point, 1 minus 2, and this is our second line. So let me draw it better. So what is the solution of our system geometrically? It's a couple of numbers, x and y, but they are the numbers that represent the intersection, the x and y coordinates of this point of intersection of the two lines. And in fact, this should be, as you can see, it's halfway from 1. In fact, if you solve it analytically, you get x equals 1/2, whereas y equals 0. And if you substitute them into this equation, you get indeed the equality holds. And that's fine. This is the first picture we learn when we see linear systems for the first time. And this is what Gilbert Strang is an amazing professor at MIT calls the row picture. Why the row picture? Because we're considering the row of the equations. But now let's take a look at another view that is even more interesting. So what we're going to do is kind of rewrite this system in a more compact way using matrix and vector multiplication. So what we have here, we have two variables, x and y, and we have their coefficients, and on the right we have the terms that, you know, they're not multiples of x and y. So we might want to arrange our system in the following form. So we put here the coefficient of x, here the coefficient of y, and the row basically tells us what is the equation we talking about. So we have -4, -1, we might put some parentheses just to, you know, have a nice notation, times x and y, because these coefficients multiply x and y, and we write it vertically probably because it's more comfortable. And if you have several variables, you know, it would take a lot of space if you wrote it horizontally. And this equals 1 minus 2, another couple of numbers. Now, these objects, mathematical entities here, are called vectors. And as you can see, they're basically a grid of two numbers. Now, what this equation is telling us is that this matrix times this vector equals this vector. How do we define matrix multiplication? Well, we define it so that we get back to the original system. Basically, these two are the same, they have the same meaning. The first two coefficients in this row are the coefficient of x, that is 2, and the coefficient of y, that is -1. So the first row times this vector here should give us 1, that is this value here. Whereas the second row times x and y should give us -2, the second equation. So every row of the matrix represents the coefficients of x and y's of the two equations. But what if we take a look at this matrix vector multiplication in another way? As you can see, let's go back to our original system, because this is where we have to start. We can take another look at the columns. What I mean by columns is, as you can see, there's a column here. There are two coefficients multiplying x, whereas here there are two coefficients that they're the same, they're -1, that multiply y. But here we have something that's a vector, two numbers, and if we multiply a vector by a scalar, we get each component multiplied by that scalar. So what we want to do is to take a look at this system in the following way. We put the coefficient of x in a vector, in a vertical vector that multiplies x, plus y that multiplies its coefficients, so -1, -1, and then we have 1 minus 2. And as you can see, this is the same as our original system, because if we do this multiplication, we get 2x and the second component 4x, and plus minus y equals 1 minus 2, and we can sum vectors. And how do we do it? Well, we do it component wise, so we sum each component, and at the end we get 2x minus y as the first component, and 4x minus y as the second component, and this equals 1 and minus 2. As you can see, this is the same of our system. It tells us that the first line has to be equal to the first line on the vector on the left, and the second line has to be equal to the second line on the other side. So this is the picture of basically linear systems, matrix vector multiplication. And that's another thing we could do. We could find what do we mean by this sum here in terms of graphs. So let me show you what I mean here. Now we always have our x and y axis and our x and y plane, but now let's take a look at this equation here in another way. So this is a vector. It basically has two components, an x component and a y component. It's basically a point or an arrow. It can be, drawn in both ways, but arrows are better because they gives us a clear picture of what is going on. So let's draw this vector. It has the first component is the x component, so this is 1 and this is 2, and the other component is, sorry, this is a minus 4. I forgot about that. Sorry guys, I apologize, I forgot about the minus sign. Let me check. All right, everything else is fine. So minus 4, so this is 1, 2, 3, 4, this is minus 4, and we can draw our vector like this, as an arrow or a point in that point, but it's better to write it as an arrow starting from the origin. Now let's draw the second vector, the vector minus 1, minus 1. So this is the x component minus 1, and this is the y component minus 1. So this is our second vector. So this is in green. Now we can write the third vector, this vector 1 minus 2. So the first component is 1, the second component is minus 2. So it kind of goes in this way, yes. Now, what is this equation telling us? It is telling us that if we take the first vector, the yellow vector, and we multiply it by some constant, some scalar x, why do we call them a scalar? It's just a number. Because if you multiply a vector by a number, you multiply both components by the number. And that results in a scale of the vector, so it kind of gets longer, or it could even get flipped because of that multiplication. If x is a negative number, it will flip the vector. So it's kind of a scaling of that vectors. And if to that vector you add some other scalar times a vector, and these two scalars are the values we're interested in that solve our linear system, we get the vector 1 minus 2. Now, there's only one combination of, at least for this system, of numbers x and y that if multiplied to these vectors that has to be added gives us this blue vector. Now you can see from the picture, the blue vector is kind of on the same line, on the same straight line of the yellow vector. So it's just a real scale of that yellow vector. So we don't even care about the green vector because it's in another direction. So let's take a look at the component of 1 and minus 2. If we put x equals to 1/2, so x equals to 1/2, what happens is that the vector 2 minus 4 gets scaled into the vector 1 minus 2, that is our solution of the system. And the vector y has to be multiplied by 0 because it is in another direction and we don't care about that vector. And not caring about a vector means multiplying it by 0. So if we had to rescale a vector, the vector 0, 0, we get 1 minus 2. That is our answer. And if the vectors were not in the same direction, you could have used the rule of the parallelogram to add vectors. So this is called the column picture because, as you can see, it deals with the columns of the vector. So in the next video we're going to talk about matrix multiplication, that I think is even more interesting. So if you enjoyed this video, please subscribe to my channel, leave a thumbs up and share this video with your friends. Until next time, bye.